The most recent one?
Yeah.
Yeah, I was going to do it today. I was super busy in my office today. I had students nonstop the whole time I was in it. Oh, no, I mean, normally I have them back the next class, but today I just didn't. So next week, the grades might get posted before that. The grades might get, I mean, I may grade it tomorrow, but I'm not going to see you till next week. So, okay, yeah, it's 1 o'clock. Okay, so who texted me about differential equations? That was you? Okay, I didn't look at who sent it. I can talk to you after class. I have a little bit of time. Did you figure it out or no? Still stuck? Okay. All right, so from last class, you know, we were talking about in Cal 1 we had 2 different methods for finding max and mins. So just to remind you, in Cal 1 we had this idea of an absolute or global maximum and minimum value of a function on a closed interval. So I wanted you to see this visually. Remember that in Cal 1, when we were dealing with functions, we would define that if we define them on a closed interval, let's say a, b, then you're imagining that you're taking each point in here and you're plugging it into the function, you're getting something, right? Getting something, getting something. If you do all the points together, you know, you get some curve, whatever it does. And as long as this function is continuous, then that function must achieve a highest and lowest point. So long as it's continuous, that's guaranteed. But the domain, okay, the domain of this is this closed interval, right? It's everything in here. So imagine it's just like this little, it's just a line segment, isn't it? It's just a line segment from A to B, and we imagine we're taking that line segment and we're mapping it into the function, and that line segment up here on the function becomes a curve. I need you to kind of understand that with what we're about to do, all right? So here we go, today's stuff. I'll talk about the exam at the end. This is it. All right. So last class, what happened was I gave you a function. We'll take a look at it. Gave you a function. I think this was the last one we did. No? Did we do that one? We did this one, right? Okay. So that was the last one we did. And the idea was I gave you a function of 2 variables, which we know creates some sort of surface. And then we found the critical points by setting the first partials equal to 0, and sometimes we'd set them equal to each other. And this would give us a list of points that would be candidates for any max and mins that we would have. But we're looking for local max, local min. Okay, so like locally highest and lowest points. But our domain, there was no restriction. Like, I'm not restricting your domain here. The only restriction we have is the implied domain of the original function. Like, you can't plug in 0 here for x or y, right? You can't have x or y be 0. But other than that, there was no restriction on the domain. Agreed? And so we went through and we found the points, then we calculated capital D, and that either gave us local max, local min, saddle, something like that. Someone did ask, what happens if you calculate D, capital D, and you get 0? And basically that tells you nothing. All right, so if that ever happens and you calculate capital D, you get 0, then the test fails. That capital D computation is useless to you. All right? So today we're going to change the game. We're going to kind of do it like I just showed you the picture from Cal 1. Before we can do that, I need to make sure we have some ideas, some definitions understood. First of all, what is a closed set in 2-dimensional space? So we know, like in algebra and pre-cal, when we talk about a closed interval, like the closed interval, let's say 0, 2, that is every single point between 0 and 2, including 0 and 2, right? So the 2 endpoints are included. But if you had this, the 2 endpoints are not included. So this is called a closed set, this is called, or closed interval. You can also say it's a closed set. This is an open interval or an open set. Curious, what would this be? What would we classify that as? Have you ever heard what that's called?
It's closed on one side, open on the other.
It's closed on one side, open on the other. So we call this either a half open or half closed. Yeah. Okay. right? Because like half of it's closed, half of it's open. So you can call it either one, half open or half closed. All right, but in two-dimensional space, on a flat sheet of paper, right, where we have both the, two axes, let's say x and y. Now remember, the x and y for us is actually the ground, right? Our x-axis, our y-axis, so we're talking about the ground here. A closed set on the ground in the xy plane is going to look something like this. So it's every point inside and every single point along the boundary is included in that set. As opposed to this, can y'all tell these are dashes? Okay, so this is not closed, all right? Because you're not including the boundary. This one, you include the whole boundary except for that one point. And because you don't have that one point right there, I know it's hard to see it. That's a little open circle. Because that one point is not included, this would not be a closed set. And then this one, of course, it looks like that's solid, but then these are dashed. So that would not be closed either. So to have a closed set, we've got to have every point on the interior and every point on the boundary. Okay, so now we have a theorem. This is very similar to the theorem we had in Cal 1. It says that if you have a function, f, that is continuous, so again, it's no jumps or breaks or holes. If it's continuous on a closed bounded set. Oh, did I say what bounded was? Bounded. So bounded means that it doesn't go off to infinity in any direction. Okay, so like if you look at the xy plane, let's say we take everything in the first quadrant, including the axes. So everything here and everything out forever. That would not be bounded. That would be unbounded because it keeps going forever. So the theorem is saying if you have a function, you're looking at a function on a closed bounded set in two-dimensional space, then as long as that function was continuous, right, it must attain an absolute maximum value and it must attain an absolute minimum value. Somewhere, either on the boundary or on the inside, there's some point that you plug in the function that's going to be the highest, and there's some point that you plug in that's going to be the lowest. All right? So that's a theorem. We can take it on faith, I guess, and believe it and use it. All right? Now, to find the actual absolute maximum minimum, how do we do it in Cal 1?
Find where the derivative equals 0.
Okay, so in Cal 1 we had this idea. So we would figure out where the derivative is 0 or undefined. So we called those critical numbers. And then what did we do? We took those critical numbers and did what with them? Plugged them into the original function. And then we also plugged in the endpoints, didn't we? And we compared. Do you see how that might be a problem for us in this approach? Like if I tell you to plug in the endpoints here, it's just 2 points, right? But if you have a closed bounded set, right, I can find on the inside, just like you did over there, I can find where things are happening, interesting things are happening by finding the critical points here. Just like we found the critical numbers here or critical points here, right? But then we have to look at the boundaries and compare. How are you going to look at the boundary and compare? You have an infinite number of points on a boundary, don't you? It's not just 2 points. So it seems like it's going to be not possible for us to do this, but you can do it, all right? So here are the steps. Y'all understand what I mean? That it seems like it would be a problem? Pardon?
Could you elaborate a little?
Okay, so you told me that to find the absolute maximum minimum here, what you did was you took the derivative, you set it equal to 0, right?
Yes, sir.
And you get some answers. I don't know, maybe you get like x equals 1 and x equals 3. You take those answers, you plug those into the original function. And then you take the endpoints and plug those into the original function. You look for the biggest and smallest. Okay, over here, I'm going to take the derivative, okay, of the f, but now it's a surface. Now that means I'm going to take those two partials, set them equal to 0, and I'm going to get critical points here. And maybe those critical points are in here. And those will be numbers that I will take, or points that I will take and plug back in to the original function and figure out how big they are. But then I have to compare that to the endpoints. But look, your endpoints here is every single point on the boundary, every one of them.
Okay.
And that's not just 2 points, that's an infinite number of points. So you can't, it doesn't seem like we'd be able to do this, but we can do it. Just a little harder than it was here. So to do this, here's what we're going to do. To find the absolute maximum and minimum values of a continuous function on a closed bounded set D, number one, we find the values of f at the critical points of D. Step one means that you have to take the partial derivatives, partial of f with respect to x, partial of f with respect to y, set them equal to 0, and that gives you critical points. That's what we did last class. The difference is we do not have to compute capital D. We just have to figure out what points are interesting to us. We don't calculate capital D because capital D gives us local max, local min. That's not what we're looking for. Is that kind of, Okay, so going to find the critical values, the critical points of the function, all right? And then we must find the extreme values of the function along the boundary of D. This is going to be the hard step. And then we compare the two and we say the largest that we get from those two things is going to be our absolute max and min. So let's run through an example. You'll see how this all works. And you see it's somewhat problematic. So here's our first example. We want to find the absolute max and min values of this surface, f of x, y equals this, on the closed triangle with vertices 1, 0, 5, 0, 1, 4. All right, so let's get a visual of what's going on here. So I have a surface here, right? And I'm trying to find the absolute maximum and minimum of this surface, but I'm restricted. I'm not allowed to plug just anything into this function. Remember, our domain's on the ground, right? The only things I can plug in are things out of this closed bounded set, the triangle with these vertices. So I have a picture here. So this is the ground, okay, everyone? This is the xy plane on the ground. Those points are getting mapped up into the surface, and only these points. So if I imagine doing that, see, I have it kind of drawn out here. See, this is that triangle in three-dimensional space. Here's the triangle in two-dimensional space, right? So if I take just the points here, I think I know you don't like it when I turn the lights off, but just so you can see this a little better. So if I take just the points on this triangle and I plug them into the surface, all right, so here's the surface, right? That's the whole surface. But if I just plug the points in the triangle into that, we're talking about just that part of the surface. Let me bring the surface out of here now. So do you all see that this green patch is the part of the surface that's created if we just plug the points in from the triangle? Y'all see that? Some of the points, when we plug them in, go up. Some of the points, when we plug them in, go down. It just depends on the function itself. So some of the surface is above the xy plane, some of it's below. Do y'all follow me? You all see that? Is it obvious to you? I think I'll make it bigger. Is it obvious to you that we would have an absolute max and min of this thing?
Yes.
Yeah, I mean, it's got to have a highest point and a lowest point. And we need to find out what they are. So we have some answers here. Here they are. We actually have 2 points that are equally high, here and here, and we have 2 points that are equally low. So what are they? Where do they happen? That's the question. Understand? Now, so the way we're going to do this, I'm going to show it to you visually first. We're going to calculate the partials and set them equal to 0, the two partials. And this is going to identify all the places on the surface where we might have local maxes and mins. So that might give us little hilltops and valleys. Okay? And what we're going to do is anywhere where these are true, we're going to go and check them. We're going to go test those points. And we're going to see, is that going to give me a highest or a lowest? But we'll identify the points first with this. After that, then we need to go and look at the boundary. That's the hard part. So the way we break it down is this. I will define 3 curves. Well, in this case, 3 straight lines. Do you agree that this right here to here is a line segment? And if I just take just that line segment and plug that into the function, then here's what it would look like. It would be that blue edge of that green surface, wouldn't it? So if we just kind of line up our eyes properly, this almost looks like a Cal 1 problem. We have a closed interval, and we have a function we're trying to find the max and min of it. Does that make sense? And then we have another line, so we'll look at that. Then we'll have to go along a second boundary. That boundary is along this back side. And see, looking at it from this perspective, that again is back to a Cal 1 problem. You have a closed interval, and you have a function right there. Does that make sense? And then we'll have to go along the third boundary, which will be this edge right here, which corresponds to this side. And again, that looks a lot like a Cal 1 problem again. And that will have moved us all the way around the closed bounded region. So this is going to break down for us, for this problem, it's going to be 4 things. First thing, compute the partials, figure out any critical points. Second thing, move along one boundary, figure out any critical values. Then move along a second boundary, and then a third boundary. So once we get all of that done, we will compare all the different values and then pick the highest and lowest out. It's a lot of work. Would you agree? Yes. That seems like a lot of work? All right, so let's see if we can't do it. All right, we'll refer back to this picture. I'm going to just copy this function down. We have the function f of x, y, equals 3 plus xy minus x minus 2y. And then, you know what? If I make that smaller, I can just leave it up there. That's what I'll do. Can you all read that okay? Okay. Turn that light back on. I'm falling asleep. Whoa. Whoa, what happened? All right, so first step, I am going to calculate some partials. So what is the partial? So right now, what am I trying to do? I'm trying to find the critical points. All right, that's my first step. Find the critical points. All right, so partial of f with respect to x is what here? Y minus 1. And then the partial of f with respect to y is? X minus 2. We all in agreement there? Now we take those and we set them equal to 0, because that's how we determine critical points. So if I set this equal to 0, I get one solution there, right? Y is 1. And if I set this partial equal to 0, I get one solution here, x is 2. So I only have one critical point, don't I? Right? It's the point 2, 1. The only way to make both of those partials equal 0 at the same time is to be looking at the point 2, 1. Now, eventually, I will plug this point into the original function to see what its value is. All right? But I have to make sure that this point lies within the region we're talking about. Because right now, this computation has no idea we're only allowed to be in this little triangle, right? So does this lie in our triangle? Let's take a look at our triangle. I'm going to draw a picture of it real quick. I know we had it up there earlier, but it's the point 1, 0, which is here. 5, 0, 2, 3, 4, 5, 5, 0. And then 1, 4, like this. And does the point 21 lie in there?
Yes.
I think we can visually inspect that and see that the point 21 does lie in here. So the point 21 is in here. And so therefore, I'm going to put a little check mark that that lies in our region. If you were to compute this, to get these critical points, if you were to get multiple points, any of them that does not lie in the region, you would throw out. You wouldn't be concerned with because those aren't getting mapped into the surface, right? It's only stuff from inside here and on the boundary. All right, we good?
It just so happened that this problem, we only have one critical.
We only have one in this particular problem.
So there could be others where we have a bunch of.
You could have 5 of them.
We only
Yeah.
choose the ones where they're inside the triangle.
They have to be, well, inside the region. The region may not be a triangle, but yes, within the region. Okay? All right. Next step. We need to find the extreme values along along the boundary, right? Let me turn my phone off here. I forgot to silence this earlier. Okay, that's enough. There we go. All right, but our boundary is a triangle, so it has 3 different sides, and so we have to move along each side. That's the easiest way to get around our boundary. So I'd like to now take a look at our boundary, and let's label it. I'm going to call the line segment going from here to here, I'm going to call that line segment L1. The line segment going from here to here, I'm going to call it L2, and the line segment going from here to here, L3. Does that make sense to you? 3 line segments. So let's talk about L1 first. Along L1, God, I can't spell today. Well, I can't spell any day, but I'm having an exceptionally bad day. Okay, along L1. All right, so tell me something about L1. If you are a point anywhere along L1, there's something very unique about you. What is unique about any point that lives on L1?
You lie along the line x equals 0.
Y equals 0, right? So your y coordinate is always 0 there, isn't it? So all points on L1 look like this. X, 0, because the y coordinate has to be 0, right? You have an x coordinate, right, whatever that is, and then your y coordinate has to be 0. But there's even more. With a restriction on x between 1 and 5, right? We have that further condition here. Y'all see that? Now, why is this important? This is important because now what we'd like to do is we'd like to take all these points along L1 and map them up into the surface, right? And see what they become. But they all look like this, right? Go ahead. You look like you want to say something.
So if we substitute y for 0 into our original equation, we will basically get the trace of that surface along that line. And as long as we keep x restricted between 1 and 5, we'll have it along that line segment.
That's right, exactly. So what we're doing is I don't know, you said it. You said it. Yes, that's exactly what we're doing. I like the word trace. We are going to find the trace of this into the function. Or if you look at that trace and map it back down to the domain, it's that line segment. But the really great thing about it is that, watch what happens. If I take my original surface and I actually plug in points along L1, they all have to look like this, right? Then go into the function, replace y with 0, leave x as x, and what does the function become? Just 3 minus x, right? And now if you just kind of squint your eyes and imagine that I came into class today and I gave you a function of x, and told you it was equal to this, right? Because it's only a function of one variable now, right? If I told you that the function was 3 minus x, and it was restricted between 1 and 5, and asked you to find its absolute maximum and minimum on that closed interval, you could do it. Because that's a Cal 1 problem, right? That's a Cal 1 problem. So what we're going to do now is Cal 1. I'm going to find the absolute max and min of this function on that closed interval. Make sense?
Sure.
Okay, so now I find the absolute max min on the closed interval 1, 5. Now remember, this is x is between 1 and 5 here, right? X is between 1 and 5. So how do we find it from Cal 1? We just talked about it at the beginning of class. We take the derivative of that, and the derivative of that is -1. And then what we do is we take that derivative and we set it equal to 0, right? But it's never 0, right? Which means we don't have any critical numbers. However, because we're doing the max and min on a closed interval, the next thing to do would be to evaluate the original function where? At the two endpoints, right? So we're supposed to take anything we get here and then our endpoints and compare all of them. But we don't have anything from this. Just so happens we don't in this particular condition. Like along L1, we don't have anything nothing from here contributes. But we still have the endpoints. Got it? So now what I'm going to do is this. I would like to test the endpoints. So to test the endpoints, I only put this blue one up here so you could see we've got this down to a Cal 1 problem. But to test the endpoints, I'm actually doing this. F of x is 1, right? That's one endpoint. And then the y coordinate was 0. Why is it 0? Why is the y coordinate 0? Yeah, because we're on L1 still, right? We haven't moved off L1. So now just go back into the original function. Or, you know, it still works here, too. You can just replace that with 1. And what do you get? 2. All right? And then plug in the other endpoint. And that's going to look like 5, 0. And when you plug 5, 0 in there, you should get -2. All right. So what have we concluded here? We've basically said that if you take yourself and you restrict yourself to just L1, which is this one, and you plug just those values into the surface, you get that edge right here, right? You get that edge right there, and we are able to determine that the highest value it ever becomes is 2, and the lowest is -2. And that corresponds to that corner and that corner. And the reason you didn't have this, the reason this never gave you an answer is obvious. It was a straight line, right? So you can never have a derivative be 0. Your derivative is constant, so it's a straight line. Okay? So now we move on to L2. And then we go to L3. And then once we have them all, we compare them all. And we still have to go back and look at this one too, right? It's a bit involved, right? All right, so let's look along L2. Let me save this. I'm just going to put this information over here on the side here. We had f of 1, 0 was 2. F of 5, 0 was -2. And I need to do this one, right? I'll put it at the top of our list. This one we never plugged in, did we? I'll get it later, okay? I'll get it later, but let's not forget we have that point to look at later. All right, so now let's go along L2. All right. Now, if we're on L2, if we're on L2, then it's not as simple as L1 was, because on L1, y was 0, wasn't it? And because y was 0, we were able to rewrite our original function, and so that it turned out to be 3 minus x, so it was a function of one variable. Is there a way that we can go along L2 and still be able to get our original function to be a function of one variable so we can use cal1?
Yeah, the equation for that line is y equals negative x. Negative x.
Yeah, we're going to find the equation of the line. That's what we need to find, is the equation of this line. So we have 2 points, right? The point here is the point 1, 4. The point here is 5, 0. So we're going to go back to this good old formula from college algebra. Used it in Cal 1 a lot. This is the equation of any line. So we just need the slope first. So rise over run. You just get -1, I believe, right? So I'm just going to let you do that. This is -1 for the slope. And then I need to pick either point as my x1, y1. And I'm going to pick what I think's the easier one. I'm going to do this one, because y2 would be 0, and then y1 would be 0, and x1 would be 5. So the equation of this line is y equals -x plus 5. So that's the equation of L2, right?
Yep.
Now, do you have any restrictions on L2 for me? Like, if I'm going to draw just L2, just the segment, can you give me some restriction here?
1 to 5.
What's from 1 to 5? X must be restricted between 1 and 5, because that means we'll go only from 1 to 5. We'll only draw that piece of the line segment, right? All right. Now, there's something else we have to do here. We have to look at what all points along L2 look like now. All points along L2 look like what? In the previous problem, it was x0, right? X comma 0. But what do the points along L2 look like?
X comma negative x plus 5.
X comma negative x plus 5. Perfect, because the x coordinate is whatever the x coordinate is. The y coordinate is, well, this, right? So this is what all ordered pairs on L2 look like. Every single point you would pick off L2 would have to have some x coordinate, and then this would be, we were forcing our y coordinate to be this because you have to live on the line, and your x has to be between 1 and 5. Do you see? Now what we'll do is we'll take all those points on L2 and let's push them up into the function. So when we push those into the function, let's see what we get. So, comma, f of x comma negative x plus 5 will be, so I need to bring my function back up because I need it. Where the hell's my thing? So our function is 3 plus x times y, right? But y is negative x plus 5, and then minus x, and then minus 2 times negative x plus 5. See what I'm doing? I'm leaving all my x's as x's, and I'm replacing all my y's with the y coordinate on the line. And yes? Okay, so let's clean this up. What does this become? See, 3 minus x squared plus 5x minus x plus 2x minus 10. Let's collect like terms. And let's put it in descending order just because, why not? So negative x squared
It'll be
plus 6x
minus 7.
minus 7. So right there, just with that, here's what I can tell you. If you take all the points along the hypotenuse of this triangle right here, L2, and you map them up into this surface, it's going to draw a parabola that opens down. Like, that's what it's going to look like. And that's what it did look like, right? Remember the picture here? When we went along L2, let me bring L2 in here. Take L1 out. See along that back side there? You see the parabola opening down? But if you didn't have, see, we don't have the picture. Like when we're working a problem, we don't have the picture. But now we know that's actually what's happening. Now, that parabola, I know I can find a max and min. I'm on a closed interval, so I'm going to use closed interval method. I'm going to take derivative of this. I'm going to set it equal to 0, see where it's undefined, then compare it to the endpoints, all the same game. This time we're going to have a derivative that's going to give us something, right? So let's take our derivative. So, yeah, are y'all okay? Let me see. How do we want to do this? What kind of notation do I want to use here? Do we want to kind of tell ourselves we're calling this a function of x now, and then over here write down like f prime of x is equal to negative 2x plus 6. Is this okay to do it this way? And just remember that really it is a function of two variables, but because we're on L2, it's a function of one. That's all right to write it like that? Okay, so we take our derivative. Now we set it equal to 0. And when we set that equal to 0, we get only one solution. And the solution is what? 3. Okay? So it's 3. So what are we supposed to do now? I forget. We're supposed to plug that number into what? The original. So I'm supposed to figure out what f of 3 is. But I'm also supposed to plug in the endpoints. And the endpoints are 1, 5. So I need to plug in 1 and I need to plug in 5. These are your endpoints. I was going to erase the eraser. Get that out of here. Why aren't you moving? There you go. All right. So when I plug 3 in, bless you, when I plug 3 in, where am I plugging it in?
Very first one.
So that one. No, sorry, not that one. That one?
Yeah.
This is our original function, right? This is what we said f of x is to us. It's this function. We don't plug these points back in, we don't plug them into the derivative. We plug these into the original function. So I got to plug 3 in here, then 1 in here, and then 5 in here. So what happens when we get 3 in there? Negative 9 plus 18 minus 7, so 2? 2, we get 2. What about when we plug 1 in? Negative 2. And 5. Negative 25 plus 30 minus 7. Did I do that wrong? It's negative 2. Negative 2. Okay, so now let's see if we can, from this information, let's see if we can't add to our list over there now, right? Because what we've done is we've figured out those 3 points. We know that the highest one is 2, and then those 2 bottom corners look like they're negative 2, right? But in terms of our function over here, this list that we're creating, let me write it here first before I put it over there. Here's what this first one tells us. When we're at the point 3 something, we get 2. So where are we? 3 what? Because we have to be along L2, right? This is just the x coordinate. What's the y coordinate? Negative x plus 5, right? So if I plug in 3, negative 3 plus 5 is 2. Understand? This one tells us that when we were at 1, and then again, plug 1 into this, that's going to be negative 1 plus 5, that's 4. So when we're at 1, 4, what value do we get? Negative 2. And then this last one is when we are at 5, what? 0, right? We're at negative 2. Does that make sense, how I recovered these points? Now, do y'all see that we have an overlap here? Do y'all see that we already did that one? Do you see that's already there? Do you realize why it's there? Yeah, L1 and L2 share that point. So both of those, we looked at both of those, we've looked at that point twice now. And when we do L3 this way, we're going to do that point up there twice. You know, we will have done that point twice also. And this corner too is going to get picked up again. So, yeah. Okay, you ready to go along L3? I think L3 is going to be easier than L2 in terms of the algebra and calculus, but the notation's a little weird. Now this has only taken us, what, 35 minutes so far? All right, here we go along L3, sorry. So along L3, I did it again. Damn, I don't know what's going on. Along L3 now. So what do all the points on L3 have in common? What do they look like? There's something. Yes, they all look like 1 comma y. So all points along L3 look like the x-coordinate is fixed at 1, but the y-coordinate's not fixed. So y is free to be y. And we do have a restriction that y must be between, careful, it's the y-coordinate, so between 0 and 4. Okay? So y has to be between 0 and 4. See the difference there? I'm looking at the y-coordinate as opposed to the x-coordinate. Pardon?
You're at 1.
Yeah, I did. Did I say 0? Yeah. What's going on? Someone put something in this, I think, today. Or not enough. Now what?
Now we plug in x equals 1 into the original f of x and y.
We're going to plug in x is 1 and y we're going to leave as y into the original function. So this is the part where we're taking those points, mapping them up into the surface to see what they become. So I look at what is the original surface f of 1y, and this will be, I've gotten rid of it again, 1 for x, y stays y. So 3 plus y minus 1 minus 2y, which turns out to be 2 minus y. Now, we can look at that right now and we could determine just right off the bat that that's a line. In terms of it's linear, right? This is a linear expression, so it should draw me a line up there, which means it's not going to have any critical points in the middle, right? But I want you to see the bigger picture here. The bigger picture is that we have now taken this function and it is now a function of a single variable y. And so using calculus, we can find the max and min of this on this closed interval. See, but we're using y instead of x, but it's the same game. Same exact game. So we sit here and we say, all right, what would f prime of y be? Well, -1, right? Well, when does f prime of y equal 0? Well, it doesn't, right? And so all I have to do is evaluate the original function at the 2 endpoints. And what are the 2 endpoints? Zero and 4. But these are our y values, right? Not our x values. So let's plug those in to this little function right here. And we get 2, and the other one we get is -2. And that's what we were expecting, because along L3, we knew that any of those points mapped into the surface gave us a straight line. So the only 2 numbers that are going to matter are these two endpoints. And so it should give us those values we got earlier. So can you tell me now from these two what those are on our function of two variables? We know that those are the y coordinates, so 0 and 4 here, but what are the x coordinates? Yeah, because we're on L1, because we're on L3, 1, 1, right? I mean, we knew that to begin with. So if you plug those in, let's see, we already have those. 1, 0 was 2, and 1, 4, I thought we had 1, 4. We did, didn't we? It was -2, but I didn't add those other ones to our list earlier. So this is 2 and -2. We are not done. We never figured out what the function's value was at 2, 1. Remember that critical point we found from the very beginning? We never plugged 2, 1 into the original surface. Should we do that now? What was f of 2, 1? So 3 plus 2 times 1 minus 2 minus 2 times 1? Yeah, I think I did that right. So what do we get here? You just get 1. Okay? You get 1. So, what is the absolute maximum value of this function restricted to that triangle? 2. What's the absolute minimum value of this function restricted to that triangle? -2. Now, it happens at different points, right? We got 2 at a couple of different places, and we had -2 at a couple of different places. So that's why in our picture, that's why we have we have 4 points. There's 2 places where it was 2 and 2 places where it was -2. All right. That's fun. That took 40 something minutes. I told you these would be a little bit more involved. Have I delivered? Yes? Let's do another one. I think we're going to try and do this one without a picture. We're just going to go for it and see if we understand this now. Were there any questions on that?
The answer was just 2 and -2.
Pardon?
The answer was just maximum.
Yeah, the absolute maximum was 2, the absolute minimum was -2. If someone asked us where they occurred, we could go back to our list and figure out like the ordered triple, like the x, y, and z coordinate that gives us the 2's, and the x, y, and z that gives us the -2's. All right, so find the absolute maximum and minimum values of this function on the rectangle D equals, so this is the way we read this. This is a rectangle, we're calling it D, which is the set of all ordered pairs in two-dimensional space. So it's basically all the points on a flat surface where x is bigger than or equal to 0, less than or equal to 3, and y is bigger than or equal to 0 and less than or equal to 2. So what does that look like? What is it? Here's 3. Here's 2. Isn't it just this little rectangular box right here? That's it right there. It's everything in between where your x is between -0 and 3 and your y is between 0 and 2. It's everything in between and all the boundaries. So you should probably at this point have a slight little kind of regurgitation feeling, knowing that you have to go L1, 2, 3, and 4, right? You've got to go 4 lines around this thing, right? But that's not where we start. Where do we start? Find the critical points, right? So we'll start with that. Critical points. And to do that, I take the partial of f with respect to x, which is 2x minus 2y. And then the partial of f with respect to y, which is negative 2x plus 2. So those are my partials. Which of those would you like to set equal to 0? Which one looks easier? The bottom one, right? The bottom one, we're going to get a solution. So when you do this one equal to 0, you get only one answer, and that's x must be 1. And once I know what x is, what? You plug it in here. So your second part, or your partial with respect to x equals 0, that equation actually becomes 2 minus 2y equals 0 because I've replaced the x with 1. So that, oh, we get 1 again, don't we? 1, 1. So the critical point is 1, 1. Is this point valid?
Yes.
Yes. Why is it valid? Yeah, it lives in here, right? So it's valid. Check mark. Hey, last time we waited till the very end. Let's just get the value of this now, okay? That way we don't forget later. So what is f of 1? What is f of 1, 1? Is it 1? Yes? No?
Yes.
Yeah, so this is going to be 1. So 1, 1, 1. Step 2, find extreme values on boundary. Well, how to do this? L1, 2, and it doesn't matter how you label them. It's up to you. Okay, if you want to call that L1, go for it, all right? I'm not sure why. I want to call that L1, 2, 3, and 4. I don't know why. You can do it however you want. I'm going to do that, though. L1, L2, L3, L4. Now, this will take us a little while to do, right? So do you all want me to work through the whole thing or just do like a couple of the boundaries? It's kind of up to you.
Whole thing.
You want the whole thing? Okay. All right, so L1. I'll move a little faster, though. On L1,
Take the x is 0.
hold up. I'm asking you. Adam. There you go. Adam, on L1, tell me about all the points on L1. What do all the points on L1 look like?
Y is 0,
Okay.
x is limited to 0 to 3.
Okay, so x is going to be x still, and y is 0, and x is between what? 0 to 3. Good. Okay, so all of our points look like that. We're going to crank through everyone. Aaron.
Yes.
Okay, what next?
Next, we are going to find the derivative.
Not quite.
I'm going a little bit ahead of myself.
Yeah.
L1. We are going to find f of x 0.
Okay, good. So we're going to take those points, see what they look like when we plug them into the surface. So map them up in, and oh wow. What is it? When you plug in x0 into the original surface, we get what? X squared. Right? Okay. Jonathan, you're up. Jonathan, now what? Yes. Take the derivative of this. So we're treating this as if it's just a function of the single variable x. So now we go through the Cal 1 steps, right? We take the derivative of this, and that's 2x. And what do I do with that? Once you find the derivative? That's all right, go ahead. Find where it's 0. So where is that derivative equal to 0? So set 2x equal to 0. So you get x is 0. Right? Okay, now, Cameron. Where's Cameron? No Cameron. Audrey. What now?
Don't we put that into the original?
Okay, you're going to take 0 and plug it into the original meaning this one, right? And you said in the endpoints. Perfect, yep. So we're going to go f of 0, f of, 0 again? We don't need it twice, do we? Okay, so 3. And what do we get there, Audrey, when we do that?
We just get
9 here and 0 here, right? Okay. Now, in terms of the original surface, these 2 points correspond to something on the original surface. It's the point, let's see, it's f of something something and f of something something. So what is this ordered pair that corresponds to this? 0, 0. And this one? 3, 0, right? And that gives us 9, and this one gives us 0. Why are these both 0? Because remember, we're on L1, so all points look like this. And we had critical values happening at 0 and 3. So these are 0 and 3, and it spits out 0 and 9. All right, save those for later. No, I'll save them right here. We have f of 1, 1 was 1. That was that one. We have f of 0, 0 is 0. And we have f of 3, 0 is 9. See, I'm making a list now of all my candidates for my global max and min. Ricky. Next. Go to L2. What do all the points on L2 look like, Ricky?
L2, the x is at 3 all the time.
The x is always 3.
And then the y is free to move.
The y is free to move between
0 and 2.
0 to 2. We all like that? L2, x is 3, y is free between 0 and 2. Okay, now I want to go through everybody, so let's see. Short and to the point. Milton, what now?
Take the partial with respect to y.
We don't have anything to take a partial of yet. We don't have anything to take derivative of.